Hello and welcome to today's tutorial. So today we will going to discuss on the power spectral density of a random process. So power spectral density is very important in the analysis of any signal sense system or in case of a random process or if it is a wide sense stationary process. Because whatever the feature, the time domain features that we will see here may not give the uh, all the necessary information that is required. For example, the mean and the autocorrelation is the features of the time domain sequence, but at a times we require the features to be extracted from the frequency domain as well. So then we need to transform our the process or the signal to a frequency domain. Then we will study about the power spectral density. Now let us switch back to our screen and let us see that the definitions of power spectral density and what it is required. So as I have told, the power spectral density will give the information about the frequency content that is involved in the signal. Now if we take this signal here, which is an observation, so just remember that we are not considered the random process yet. We are just considering a one-dimensional signal here, that is x of t, and this x of t is, say, it is varying from minus infinity to plus infinity. And if I want to find what are the frequencies that are involved, because there are a lot of variations here and we cannot say what frequency is exactly involved because it is not a pure sinusoidal wave. If it is a pure sinusoidal wave, then we can say there is only one frequency component involved. But when there is a variations of the signal involved, then there are many frequency components that will be there, and we need to understand what frequency is dominating over the other frequency. So in such cases we'll go for power spectral density or applying of the Fourier transform. So now if this signal is varying from minus infinity to plus infinity, then I cannot apply the Fourier transform for this case. For example, if I write this mathematically, then the signal is, say, if it is x of t here, magnitude of it into dt. If the signal is not integrable and if the value of this integral is not less than infinity, then we cannot apply the Fourier transform for this case. So for that is why we used to take always a signal with some fixed interval of time, or we'll apply a certain window for this signal. So in practical case, there is no such signal which is from minus infinity plus infinity. Always we take, say, every signal has some start point and end point. Otherwise the nature is always an infinity. It's always exists before us and even after us also. But otherwise, when we take any data for recording, we start recording at some time and we'll stop it at some time. So likewise we will consider this, the start time and end time. Say that I take this value from the interval, say, minus t by 2 to plus t by 2. So my entire interval or the duration is, say, time t period, or the window is of time. So this window, whatever I have taken, it is of, say, time period t. So if this is the condition, then I can apply my Fourier transform and I can find what are the frequency components that are involved for the random process. So now let me write this definition xt. So xt of t is actually x of t itself, but it is for the certain interval. It is not for entire range. It is equal to x of t. So that is from minus t by 2 to plus t by 2. Here the variable is time t. So that is why it is ranging with respect to time t from minus t by 2 to plus t by 2 and 0 otherwise. So if this is the case and if it is integrable, then I can apply the Fourier transform. Now let us see the definition of Fourier transform. We know from the Fourier transform definition, so let me write here mathematically. We used to write this as x of omega, the Fourier transform. Either we can write in terms of frequency also, or we can write in terms of radians as well. So this is defined as minus infinity to plus infinity, that is x of t multiplied with an exponential term, that is e power j omega t into dt. So this is the definition of the Fourier transform, and the inverse Fourier transform is defined as, so if you want to get back the time domain signal from the frequency domain, then it is written as x of t is equal to 1 by 2 pi into integral of minus infinity to plus infinity, that is x of omega into e power j omega t into dt. Sorry, I have missed one term here. This is e power minus j omega t into dt, and this is e power plus j omega into dt. So that is the only difference here to the exponential terms, and here we will get 1 by 2 pi is the additional term. So now if you want to find the power of the signal, then the power of the signal can be found by squaring the signal and taking average of it. So again, let me repeat, the power, we are not talking exactly in terms of watt, but it is proportional to watt. So let me save this page. So this is 35. Let me get the new page here. So if I apply the power to this signal, then the power to this signal, I'll get this as, that is Pt is equal to 1 by t integral of minus t by 2 to plus t by 2 for x of t into dt, x of t in x square of t, sorry, it is x square of t into dt, because I have to square the signal if I want to get. If I just square this and integrate, I'll get energy. If I divide by the time period, I'll get the average power. So then if I split this terms, that is if I write this as 1 by t, so before splitting this term, I can also define this as equal to minus infinity to plus infinity. I can write this as xt of t into dt, because we know that the xt of t is a windowed sequence, so within that window I can write the limits as minus infinity to plus infinity. So now I'll split these terms. It is, sorry, again I'll missing this term, that is xt square of t. So then I'll get here, it is 1 by t into integral of minus infinity to plus infinity, that is x of xt of t into one more term we have, that is xt of t into dt. So now from the previous definition, I'll going to apply my inverse Fourier transform case for this one of the term. So then I'll get this as, so I'll get this is equal to, that is pt is equal to 1 by t into integral of minus infinity to plus infinity, that is I'll get xt of t into, this is xt of t into, now I'll apply my inverse Fourier transform, so I'll get 1 by 2 pi, that is from minus infinity to plus infinity. I'll get here, that is xt of j omega into e power j omega t into d omega into dt. So this is what I'll get. Now if I interchange these terms here, so I'll get 1 by 2 pi t into integral of minus infinity to plus infinity, then I'll get xt of j omega into integral of minus infinity to plus infinity, then xt of t into e power j omega t into d omega into dt. Now if you look at this term, so this looks exactly like our Fourier transform case, but only difference is that here the minus term is missing. So if the minus term is missing, then I can write this as, rather than writing as xt of j omega, I can write this as, so 1 by 2 pi t into integral of minus infinity to plus infinity, that is, then I'll get this as xt of j omega into, now I can write this as xt of minus j omega. So rather than writing as xt of j omega, I can write this as xt of minus j omega, because here the minus sign is missing. And one more term we have to remember, that is xt of j omega, xt of minus j omega is nothing but, we can also write this as x conjugate of j omega. So we can write this as x conjugate. So when we write this as x conjugate, then if I can take this as a magnitude. So let me write that term here. I'll continue that here. So then my power pt is equal to 1 by 2 pi t into integral of minus infinity to plus infinity. I'll take this as magnitude of xt of j omega whole square into d omega. So here d omega term is missing, so it is equal to d omega. So now if I compare this with my time domain sequence, now this is also my power, this is also my power equation. Now if I compare this, let me save this page here, page 36. If I compare this equation with this equation, then I can finally write this as, that is, I'll take t into pt is equal to, in terms of time domain, the mathematical definition of the power is equal to, that is, minus t by 2 to plus t by 2, that is x square of t into dt is equal to, it is 1 by 2 pi into integral of minus infinity to plus infinity, it is magnitude of xt of j omega square into d omega. So this is the definition. This is j. Please read this as j. This is magnitude. Okay. So this is what we get. And if we apply this, as of now we are considering only as a one-dimensional signal. Now if we consider this as for a random process, then same definition holds good. Only thing is that here, just to differentiate, we can write this with some symbol like this with so thick x, so representing that is a random process, and here we can write this as the capital X, again to represent it's a random process. So now if we try to apply an expectation for this power equation, then what do we get here is, if I apply an expectation for this left hand and right hand side, so this is integral of minus t by 2 to plus t by 2, that is for x square of t into dt. If I apply an expectation term here, and this is equal to 1 by 2 pi, I'll take it common outside, so an expectation of, for this entire term here, that is from minus infinity to plus infinity, so then magnitude of xt of j omega magnitude whole square into d omega. So we know that from the expectation, so this is nothing but I can write this as x of t into x of t. So there are two possibilities, either expectation of x of t is nothing but the mean of it, or I can, if I combine both of it, I can write this as the autocorrelation function as well. So now this has become a constant, and now I have to integrate with respect to time, with respect to t. So expectation of x square of t has become constant when I take the expectation inside. So then, so expectation of x square of t is now a constant. Now I am integrating only with respect to the constant term here. So then I'll get here as t. When I substitute upper limit and lower limit, then I'll get finally the term as t. So this is equal to, I'll get 1 by 2 pi into integral of minus infinity to plus infinity, and here also I'll take the expectation inside. So expectation of this is xt of j omega square into d omega. So then this is nothing but, I'll get this, I can write this in terms of the correlation function. So I'll relate this to correlation function. So 1 by 2 pi into integral of minus infinity to plus infinity, that is an expectation of the term, that is xt of j omega square into d omega. So then if I apply this limit, I can rewrite this equation in the next page. Let me save this page. So this is 37 here. So in the next page I'll write this. Finally I can relate this. Rx of 0 is equal to, this is 1 by 2 pi into integral of minus infinity to plus infinity. As the limit t tends to infinity, it is 1 by t into an expectation of x of xt of j omega whole square into d omega. So now I'll get this. So now I'll relate this to power spectral density, PSD, and autocorrelation. Remember, so far still we have not related this to Fourier transform. We are just relating this autocorrelation function with the power spectral density. So now this term, this inside the expectation term from limit till here, I call this with one more variable, that is Sx of omega. So then this term will become just 1 by 2 pi into integral minus infinity to plus infinity. It is Sx of omega into d omega, where Sx of omega is equal to this entire term, that is the limit t tends to infinity, 1 by t into expectation of xt of j omega whole square. Okay, so this is the thing. So now if we apply the Wiener definition relation, so before going to that, so let us understand one more thing here, that is, okay, let me come to this later. So by applying the Wiener Khinchin relation, Wiener-Khinchin relation, I can relate this to Fourier transform by just multiplying these terms with my exponential term, these integral terms with the exponential term. Then I can write this as, Rx of tau is equal to 1 by 2 pi, Rx of tau is equal to 1 by 2 pi into integral of, say, minus infinity to plus infinity. This is Sx of omega into e power j omega tau into d tau. So this is something like our inverse Fourier transform, and if I write this in terms of Sx of omega, so this is equal to integral of minus infinity to plus infinity. It is Rx of tau into an exponential of minus j omega tau into d tau. So these are the important relations which we're going to use in the further analysis. So now this is the Fourier transform pair of an autocorrelation function with our power spectral density. So now a few minor things that we will see, that is the complex conjugate, that is nothing but the complex conjugate of this Sx of omega is nothing but Sx of omega itself. So these are the quite a few properties, and Sx of omega value is always greater than or equal to 0 for all the range of omega, and it is a even function. It means Sx of minus omega is equal to Sx of omega. So these are the few properties of our power spectral densities, so that you have to know it. So now let me save this page here. So this is page 38. So now let us look into the plot of this power spectral density. So if we look into the plot of the power spectral density, then it will look something like this here. So this is the omega axis here. So this is omega axis, and this is the power spectral density. We call this as Sx of omega, and we'll get the two terms on both the sides with positive and negative axis here. So this we can call this as omega 1 to omega 2. The spectrum that we will get in the PSD is like this, and this is minus omega 1 and this is minus omega 2. And the bandwidth of this is defined as the bandwidth RMS value is defined as this is equal to the integral of minus infinity to plus infinity, that is f square. We can also define this in terms of frequency, remember. So there is nothing but omega is equal to 2 pi f, that's it. So it is into f divided by, we have minus infinity to plus infinity, that is sx of f into df. This is to the power of half, it means it is the square root of it. So this is the bandwidth equation of this. So now before going into the example, before looking into example, let us look into the Fourier transform pair of a autocorrelation function with our power spectral density. So let me save this page here again, page 39. So the Fourier transform pair, or so let me write here, the Fourier transform pair goes like this. So we have Rx of tau on the left side, and we have Sx of omega on the other side. So now, so cos omega c tau, its Fourier transform pair is pi of delta of omega minus omega c plus delta of omega plus omega c. So this is the relation. Now delta of tau, if autocorrelation function is delta of tau, then its power spectral density is 1, and if it is exponential of minus a with respect to magnitude of tau for the value of a greater than 0, so then it is 2a by omega square plus a square, then t and 0 here. So if it is a t of 1 minus tau, magnitude of tau into t, for the tau ranging from minus t to plus t, then it is t square into sine omega t by 2 whole divided by, so this is omega t by 2, it is omega t by 2 whole square. So then if it is omega b by pi into sine omega b tau by omega b tau, then its transform pair is equal to 1 for minus omega b for the range of omega ranging from plus omega b and 0 otherwise. So these are the few Fourier transform pairs so that we will be going to use in the examples, in the coming examples. So page 40. So let us quickly look into one example, one simple example here. So let me write it and define it here. So here it is, determine the PSD of the random process x of t. I'll define the x of t below and plot the same. So here theta is the random variable uniformly distributed over 0 to 2 pi, hence obtain average power of x of t, and if the frequency becomes 0, x of t is equal to a, that is DC signal. So obtain PSD and autocorrelation. So this is the question given here. So let me define my x of t here. So given x of t is equal to, so the given x of t is equal to, that is nothing but a cos of omega ct plus theta, omega ct plus theta. So now we have to find the autocorrelation of this function, and then we have to find its Fourier a power spectral density of the signal. So to find the autocorrelation function of this, so remember, so our definition of Rx of tau is nothing but it is equal to an integral of minus infinity to plus infinity. It is x into fx of fxt of x into dx. So since the variable here it is the theta, so therefore its density function it is f theta of theta is nothing but it is equal to 1 by 2 pi. So it is equal to 1 by 2 pi for the range of 0 to 2 pi, where the value of theta range from 0 to 2 pi. Its density function is given as 1 by 2 pi. So when we substitute here and when we apply cos a plus b formula and when we integrate this term, so I'll just quickly write, because this example we have solved in the previous tutorial, you can refer it back. So here I'll write this as a into cos of omega ct plus theta into 1 by 2 pi into d theta. Sorry, here I have written dx. It is not dx, it is d theta. Integration with respect to d theta. Now we'll apply cos a plus b formula, that is cos a into cos b plus sin a into sin b formula. So then when we integrate the cos terms and sin terms, and when we substitute the limits, so here the limits also it is not minus infinity plus infinity, the limits is from 0 to 2 pi. So here the limits will become 0 to 2 pi. So when we substitute these limits, ultimately we will get this term as a square by 2 into cos omega c tau. So omega c tau is a constant which is nothing but which is multiplied by a square by 2. You can refer the previous tutorial. In that tutorial we have solved the this example of finding autocorrelation function of this x of t. Okay, now we will look into the finding the power spectral density of this. So anyway, let me save this page and I'll copy the same question to the next page. Okay, so now let us write the formula for power spectral density in terms of frequency. You can write it in terms of omega also, that is not a problem. So this is equal to minus infinity to plus infinity. It is Rx of tau into e power minus j omega tau. So since we are written in terms of f, so it is 2 pi f tau into d tau. So if you substitute this here, so minus infinity to plus infinity, so that is a square by 2 into cos of omega c tau into e power minus j 2 pi f tau into d tau. So then from the standard Fourier transform, so this is nothing but cos term is nothing but it is delta of f minus fc. So then we will get this as this term, we will get this as a square by 2 of again half of delta of, so half of delta of f minus fc plus delta of f plus fc into df, sorry, yeah, so integral is there, so this is integral minus infinity to plus infinity, and this is equal to df. So this the cos omega c tau into e power minus j omega fc from the Fourier transform pair we can write what I'm doing, sorry, from the Fourier transform pair, so it is just only this, so finally we will get this term. So if you plot this terms on the frequency spectrum graph, so this is 0, so now f minus fc, for example, so there is some f, so f minus fc might be some term here, so that is minus fc, and its magnitude is here, that is a square by 4, and f plus fc is one more term here on the right side, so then it is a square by 4, this is fc, then it is if the fc is equal to 0 in this case, so then we'll get 2, so 2 to get cancelled, so we will get here as, so this is equal to, we will get the magnitude as a square by 2. It is not always necessary that it's supposed to be at 0, so f can be anything. So if f is not 0, so then we will get something like this. For example, if this is 0 and f is some frequency, if this is our f, then f plus fc we will get this term here, so like this, f plus fc we will get this, and f minus fc we will get the some term here, that is f minus fc, and here we will get a maximum peak, that is a square by 2, and here we may get the peaks as, that is a square by 4, so of this. Okay, so this is one of the example of finding the power spectral density. So thank you for watching this tutorial. So catch me up in the next tutorial where we are going to solve more examples on the power spectral density, and we'll talk on the autocorrelation and cross correlation in terms of the spectral density. Thank you for watching this tutorial.